a recording. It didn't save the recording. So if you're looking for Monday's lecture, there isn't one. So you just missed out. So I'm probably preaching to the choir, right? You're here. You're probably here on Monday. You're not the ones that weren't here. Anyways, so just a recap, right? The exam on Friday. It's going to be on. I gave 2 example problems on D2L. Try if you haven't had a chance to look at those. Okay, they're going to do it. We're going to do it's one kinematics problem, kind of geometry. There will not be integrals. I will not have you do any kind of integral problem on that. Okay, and then a kinetics problem, F equals ma. Right, force equals mass times acceleration. Basically everything through the homework that you just turned in on Friday. If Connor has not done so at this time, he is going to post the solutions to that homework before, maybe even before he grades it. Okay, just so that you guys have the solutions to that homework before the exam. Okay, we haven't talked about this yet. I am splitting the class. We're gonna go 50-50. Okay, because right now you're like, oh, there's plenty of room, but it's because not everybody's here, right? If everybody's here, we take up this entire space, and so half of you are gonna go, I don't know where, okay? I gotta work that out. That's one of the reasons why we haven't talked about it. So yeah, half of you, I think last time there was a room open in Reed, and so that's probably what we'll do again, is we'll do half in Reed and half here. Which group are you in? I'll post that on D2L beforehand, right? I'm gonna do it based off of your last name, basically A through like H or something like that's going over there, and then whatever. So we'll work that out, and I'll post that at D2L. Also, a review session tonight. In that review session, I'm just going to go over that practice exam that I gave you. That practice exam, again, was from COVID years. And in those COVID years, it was open books, open notes. Your exam is not open book, open notes. Okay, I had a question about that. It was a legitimate question because it says so on that practice exam that it's open book, open notes. It's not. You do get one sheet of notes though. Okay, I am going to record I'm going to try to remember to record the review session tonight. If you come to it tonight, try to remind me to do that because I think some people just can't make it at that time. It's at 6 o'clock in this room. There is something in this room right at 7 afterwards, so we got to crank it out pretty quick. Any questions about that, logistics of what's happening? Gets nervous? It's just 12% of your grade. It's not a big deal. It's not a big deal. Yeah, there obviously is partial credit. I grade all the exams, okay? And there's partial credit on stuff. So, I mean, don't count on that, but, right? And then stick to the plan. That's the idea. Okay, so the subject that we were covering right now was, and kind of just a recap of what we went over on Monday, right, was work energy, all right? Conservation of mechanical energy, right? So, and I mean, this is the equation that we're using. Kinetic energy, right, at state 1 plus potential energy at state 1 plus work being done from 1 to 2 is equal to T2 plus V2. So the potential energy and the kinetic energy afterwards, right? We're going to put all of the work stuff on the left-hand side, right? Because we're going to think of these things as like I'm at a state, work's going to happen, and it's going to take me to the other state, right? And so we're going to put all of our work on the left-hand side of this, right? And sometimes that work will be negative, right? If energy is being pulled out of the system, that it could be a negative work that's happening, okay? Right? And then we also briefly went over the solution procedure. Right? The solution procedure, free body diagram to identify any forces that are acting on this thing. Write down the work energy equation. Cross out terms we know to be zero. Expand and reduce the equation. Kinematics as required, and then solve. Right? And then we went through and did a couple of example problems. Right? Pretty straightforward ones. Right? Some of the key things there that we covered was setting different datums, different heights. Right? You get to pick what height it is. Technically, what really matters, and this is a good question that came up, is, technically this isn't at the bottom. I could have set this being equal to 0 down here. If I would have set that being equal to 0, then y2 would have a value and y1 would have another value that was on top of it, and that's fine. It's just what would happen is I would get y1, I'd have potential energy on the left-hand side of the equation, and then y2, I would have potential energy on the right-hand side of the equation, just less potential energy on the right-hand equation. But really what matters is the difference. It's the difference that matters, right? And so setting this thing up where one of them is 0, my datum is 0, you could set whatever you want on there to be 0. Okay? I could have set the top to be 0, which is totally fine. It's just at state 2, would have been a negative number. It would have been mass times gravity times a negative number because it's below. So it has negative potential energy, right? And then we just wrote out the equation. It crossed out all the things that we had known to be zero, expanded it, put in our values, solved it. Okay, same thing here, same type of problem. Okay, this is where we died last time. I didn't quite finish it, so I finished it on my phone. All right, is the cheerleader in here? Is the guy here? Is he here today? He's not here. Is that him?
Yes, that's him.
There he is. What's his name? Nate. That's the other Nate. Where's the other Nate? Oh, Nate Dogg's not here today either. What? Got you, right? You know, I was just flipping through my reels. Remember, I got some reels now. I'm a reel guy. Just because they suck, and then I'm not as addicted to them. And so I was in there, and then I get this thing, and it was just like what it's like to be at the bottom of the pyramid. And then there, I was like, oh my God, I know that guy, right? And so he's not even here for it. I think he said he has workouts in the morning, and so if he comes in, let me know. So I'll come back to this. I'll show him that I saw him. I recognize him. And then also along those lines, in my reels, I came across something for you guys. Yeah. I don't know if you've seen this before, but I thought this was pretty funny. Let's see if we can get sound.
Because it's electrified.
Why did you say that? I was getting into it.
It's either Australian. Right, so that's what I thought of you, okay? I wanted to watch the whole thing. How do I start it over? Do I just have to let's go there. Okay. Oh, I want this.
I can come to this fence over here.
Yeah.
Fuck! It's
You're not supposed to touch it.
Don't touch it because it's electrified. Why did you say that? I was getting into it and you grabbed the fence. I pointed at the fence.
The fence can't be that bad.
It's electrocuted.
How it's electric? He's just from New Zealand, he's a pussy. No, he's the cow. You think I'm not tougher than a cow?
Yes.
Cow, I'm the baby. Fuck! What the fuck?
That guy's Australian,
He's
right?
using that fence.
He's making fun of New Zealander.
That's for bulls, actually. Bull fence.
Nah, I think I've got a bad current. Let me try again.
Don't try again.
Don't touch it.
Don't touch it. Stop. You're gonna go.
Woo! Bro, it's a fucking rush. Try it again, Jimmy. Try it again. Try it again. It's a fucking
Hey!
It's a fucking rush, eh?
I don't know.
No, yep.
I'm not kidding.
Woo!
So is that what you guys do? I did. I really thought of you guys. I really did. I was like, oh, look at this. I know two Australians too. Look what they do for fun. Okay. So let's do this example here. Okay. This is a system. Okay. So we've got mass A and mass B. They're attached to a cable. You know, I don't understand. These come out of an old book of mine. Why I didn't just copy that instead of making my own drawings, I don't know, but I did, okay? I just made my own drawings. Okay, so this thing, there's a cable, it's attached to this thing over here. It goes around a little pulley that comes down, and it's attached there, and it's attached to this mass right here. And the thing is gonna slide along this rod and drop. So when B drops, then this moves to the right. And then A is attached to a spring, and so that spring is gonna stretch out over to that position over there, okay? And what we're asked to find, so this is a system. We haven't done a system yet where we got two masses floating around, okay? And they're moving kind of differently, okay? What we're asked to find is the initial velocity, right? As I would say, initial velocity of A, right? The initial velocity of A such that it comes to rest right at point C. So it's gonna be sliding along, has an initial velocity, and then it's gonna stop right when it hits that. So it's gonna basically run out of kinetic energy right when it hits that, right? Where's that energy gonna go? Into the spring, right? It's gotta go into the spring. But anyways, just that's what's gonna happen, okay? Why would this ever happen? I don't know, right? This is fun. Book just gets to make fun stuff up, okay? I don't see when this contraption would ever come about. Okay, so how we do this is we have to start out with sticking to the plan, right? We haven't done multiple masses before, but we're just gonna stick to the plan, okay? And this plan involves creating a free body diagram, okay? So we're gonna do a free body diagram. When you have multiple objects, you get two free body diagrams. You have to draw a free body diagram per object that you're dealing with, okay? So let's do that. So you could tell by the guy's accent that he was New Zealand, yeah. We cannot tell that. I heard, is it how they say fish and chips? Yeah. I can't be. Do we have accents? We have accents. Hey, Nate Dog, you're here. We were just talking about you. Man. We do have accents. Yeah. Can you talk like us? Not quite. Not yet. Give it time, yeah. Stay here another semester. You'll leave talking like us. Just articulate, intelligent. All right. So we do this per object here. Let's do mass A first. All right. Mass A is this guy over here on the left. So what we got acting on that? Yeah, gravity. Yep, gravity's going down. All right. We got a normal force acting up. This thing's frictionless. I think the problem statement says that it's frictionless. Right? Again, you could draw these things at any state. Right? So I'll draw it when it's over a little bit. And that'll be my force for my spring. Right? And then we also have this cable pulling to the right. Right? And you don't have to be as careful with these. Right? Because we're just looking for what forces are acting on this thing. Okay, let's do mass B. That should be everything on A. B, we got mass times gravity. And then we got a tension force acting up. That should be everything that's there. It's just kind of free floating out there. Okay. And again, the reason for doing this, right? These don't show up necessarily they don't show up in our work energy equations. But what we're after is just looking to see what forces in here are going to be doing work, right? And the forces doing work, right, are things that are, right, mass times gravity. Is it going to be doing work? Yes, it is doing work, but we're not counting it work. We're putting in potential energy. Don't double count it. It's way easier just to put it in potential energy, right? So these are doing work. Normal force never does work, right? It's just resisting motion. There's never any motion in the direction of the normal force. It only exists because things are not moving in that direction. And then the force from the spring, it is going to be doing work, but we're putting it in the work energy equation. We are not going to put it here, which leaves us with T, right? Is T doing work? Yeah, T is doing work, okay? T is pulling this way, and T is pulling up this way. And is T moving? You bet, right? As B drops, right? As B drops, it's doing work. As A goes to the right, it's doing work, okay? But the book spends, a good chapter or so, or not, a page or so talking about this concept, but I think it's just easy to see right here, okay? And so let's look at this a little bit on how much work those two forces actually do, okay? For that, let's do a little bit of kinematics. The geometry of motion. There's just some stuff here that it's worth pointing out. Again, geometry of motion is just, or kinematics is just like, can we look at this and observe how motion relates to each other, okay? So real quick, how would the displacement of B, how would it relate to the displacement of A? Yeah, that's right. One's going in the Y, one's going in the X. But how about the distance, the amount of distance they travel? They're the same, right? And if this cable is inextensible, right? If that cable is inextensible, which I don't know if it makes that statement, but we'll make that assumption that it doesn't extend at all, right? It doesn't stretch at all. That means that whatever distance A moves to the right, B moves down, right? And any distance that B moves down, A moves to the right. So that's the same distance, okay? Which would also tell us, what about the velocity? Well, yeah, if the displacements are the same, what are the velocities? Are they the same? Yeah, you betcha. Right, so we say displacement of A is equal to the displacement of B, right? Coming from that is the velocity of A is equal to the velocity of B, right? If we didn't make that assumption, or if we didn't point that out, that part of kinematics, we'd have too many unknowns when we go to solve the whole thing. Being able to say that those are the same velocities is huge. Okay, and that would be kinematics right there. Okay, so let me just come back up to the work really quick, right? Before we dive in. If we look at the work from 1 to 2, like I said, T is going to do work, right? So T is going to be T times delta A. Right? That's the work that this one's doing, right? T times delta A going to the right. And T times delta B. B is going to be doing work as well. I did make an error in there on purpose. This time is real. I did it on purpose. Okay. This guy, right? I got my T acting up like this, but my displacement B is going to be going down there. So what should be this? What value should this be right here? Let's do a negative, right? Because this T right here is acting in the opposite direction of movement, right? So if your force acts in the opposite direction of movement, then it does negative work, right? It pulls energy out of the system because it's acting to resist. It's moving this way, but the T force is acting that way. So it should be negative work down here. It's one of the few times that I actually make the mistake on purpose, right? So that should be minus T times delta B. If delta A is equal to delta B, what does this equal then? Oh, look. Did you see this?
No, I didn't see how'd you get that?
I was just flipping through my reels, man. I was flipping through my reels last night around 11 o'clock. And then I was just like, oh my God, it's him. I saw him. He's not lying. You're not lying to us. Yeah. Yeah, look at you. He's famous. Yeah. Right? He's on Instagram. Reels. Look at that. Look at you. Was that hard to do? It looked hard to do.
It's really hard.
Yeah.
Some of the specifics are really hard. Yeah.
How many people are above you?
The most, so right here is 2, but the most we've ever done is 3.
Yeah, that'd be tough, right?
Yeah, it's hard.
Yeah, cool.
Sorry. That's cool.
Yeah, look at that. Yeah. Can you do a backflip? You can do a backflip. Yeah, God, I mean, if I could do a backflip, I'd just do it all the time. I'd just be talking to somebody and just like, hold on a sec. Right? You should. You absolutely should. When you get done with your test, do a backflip. Yeah, do it. Someone else could do a backflip. What is it? Somebody said, didn't they say that as their interesting fact? Oh, yeah, look at you, see? You should just do it all the time. People think you're so cool. At least I would think you're cool. All right, interesting. Okay, cool. Maybe we'll do like a little talent show at the end of the semester. Okay, so oh yeah, you have a real question. Yeah.
Why do we have 2 different T's if the T is just the same in each? It's just a strength. It's just going from one piece to the other.
Yep. Yeah, I mean it's the same. It's acting on both of them, right? Like if you imagine if I pulled down on B, right, that tension force would go up and then around the corner and transfer to the other one as well, right? So they're both there. So if I'm just looking at A and you came in and I cut, remember how when we do free body diagrams, we cut it, right? If I cut it, then there's going to be a tension force going like that. If I came in and cut it, it's a tension force like that. But they are the same. They're the same tension force.
Won't they just cancel them?
That's what I'm saying. They end up doing it. I mean, when I look at the work being done right here of the whole system, work being done from 1 to 2, T times delta A minus T times delta B, those are the same, so it becomes 0. So they do cancel.
Oh. So what was the point of writing that then?
Just to show you.
Oh.
Yeah, just to show you that because it's not necessarily obvious to everyone that like those things will cancel. Because I keep telling you like, oh, make these free body diagrams. Look at external forces. And it turns out those aren't external forces, those are internal forces.
Yeah.
Right? So they're acting within the system. Because really you could do that with anything. Like if I drop this, technically I could cut it and there'd be a force and there'd be a force and then they cancel each other out. So which leads me to the statement that I'm gonna write right now. The postulate, if you will. And this is literally like the book spends a good section of that. Okay. For systems, internal non-conservative forces cancel each other out in terms of work. See book for proof. We're not going to do the proof. I think it's pretty straightforward just to see that. As you said, why are we even doing it, right? I wanted to highlight that. Okay. All right. Cool. So that's just worth pointing out. So the point is there, I guess one of the points, there is no work being done between state 1 and state 2, right? There is no, if I added a force, if I would have added something that's not gravity, if some force P that was pulling down on that thing, then there would be an external force. Or if there was friction somewhere, if there was friction along this rod, then there'd be some work there. Okay. Not done with kinematics. The last thing I want to do with kinematics is talk about the stretch in the spring, right? Because, it starts out in this position, right? And then it's going to go from this position out to this position, right? So it's going to be based off of that little triangle right there. Right? So this length right here is 0.5. This length right here is 0.8. So that's the total length of the spring. So when we calculate our S's, we got to take that into consideration. So S1 is the stretch at the beginning. Stretch at the beginning, what does it say? The unstretched length, L naught, is 0.2. So it starts out at 0.5 minus 0.2 is equal to 0.3. Right? So in the statement, this is L naught. It tells us what the unstretched length is. And so you can see over here at state 1, right, it's stretched out to 0.5. That's given to us in the problem statement. So it's stretched out to 0.5. Right? If it's stretched out to 0.5, L naught is 0.2, so how much it's actually stretched is 0.3. So it actually has potential energy in the spring, even at state A, okay? And then we'll do S2. S2. Right? And so for S2, I need to know this length right here. Right? And that's just going to be Pythagorean's theorem, right? The side squared is so 0.5 squared plus 0.8 squared. That to the 1/2. Right, the square root of those. This ends up 0.943. Right? A little bit of, again, geometry, right? The geometry of motion is under kinematics. So S2 is equal to 0.943 minus that 0.2, the unstretched length, 0.743. Just had to look at my notes to calc that. That's a little sad, right? Just take 0.2 off of 0.9. I had to go, shit, what is that? So I did get my calculator out though. Okay, so now we're ready for the next step. Next step is write down the equation, right? T1 plus V1 plus work done from 1 to 2. We're kind of all set up to do that at this point. The expanding is what's going to get us. Equation. T1 plus V1 with a leg plus work done from 1 to 2 with 2 legs is equal to T2 plus V2. I write it down every time. Even though I know some of these terms are going away, write the whole thing down. Sometimes it helps. Okay. So does it have kinetic energy at the beginning? Yes, that's what we're after, right? We're after the initial velocity such that it slows down when it hits the other end. So absolutely, it's going to have potential, it's going to have kinetic energy right there. Okay, and actually what we're after is in that term, right? Does it have potential energy at state 1? Yes, right? The string is stretched. Also, there could be a height. There is a height, right? Depending on, and I say there might be, it just depends on how we define our datums, okay? So yes, there's going to be potential energy at state 1. And then is there work being done between state 1 and state 2? We just showed that there is in fact no work being done between state 1 and state 2. Okay? And then is it moving at state 2? That's what we're after, right? The problem statement said we want to find out so it's going to stop right when it hits the end position, right? So when it stops, there's no kinetic energy. So T2 is going to go away, okay? And then potential energy at state 2. Is there going to be potential energy at state 2? Again, yes, because there's spring there. The spring is going to be stretched no matter what. But then also, depending on how we define the height, there could be potential energy in that. How about, let's define heights, okay? I'm going to define, I always like to do the bottom as being, well, let's mix it up here. I'm going to set this being y. I'm going to make this YB1 just to show that it can be, I could set it up here. I usually like to put it at the bottom, but I'm going to put it here for now. YB1 equal to 0. I'm going to find that. So you really need a datum for each object. Okay. A, is that changing in height? A is not changing in height, right? So its datums stay the same. So this is YA1 is equal to YA2 is equal to 0. I say Y isn't changing. Right, so I need one more though. I need one more. So there isn't going to be potential energy associated with gravity. They're not going to be up there at the top for object A. Object B though, it is changing, and it's going to go down here. It's going to go from where we see it there to down here. Right, and this datum, we'll call that YB2. YB2, and that one, it's going to move, right? So again, if this moves to the right, if that moves to the right 0.8, this is going to move down 0.8. Or sorry, this is going to be moved down 0.8. So this would be negative 0.8. Right? It's a negative because it's below our initial state. Right? So our datum. Our datum's up here. If you're down below it, that means it's negative. Right? So we're down below it. I always talk to this side of the class for some reason. I apologize. I had my son come once, and that's what he told me. He's like, you always talk to this side. Share the love a little bit. I'm going to try. So call me out sometimes. Like, talk to us too, and then I'll come over here. Nate, you're off a little bit. You're usually a little bit more towards the middle. That's also throwing me off today. Yeah. Okay, so there we are. Okay, so, oh yeah, what was it? What was I talking about? Okay, come back to this. All right, so we've written the equation. Now we got to expand it. All right, so let's expand this sucker out. So kinetic energy at state 1. So it's going to be 1/2 mass A VA1 squared plus 1/2 MB VB1 squared. And all of this is T1. So it's the kinetic energy of both objects. Both objects are moving, so we're going to have a 1/2 MB squared for both of them. Okay. Move on to the potential energy. The potential energy at this state, state 1. Right, the way I have it defined, right, so we're going to have some kinetic energy with this thing being stretched because S1 is 0.3, so let's put that in there. 1/2 K S1 squared. It's only one spring, so that's it. And then on mass of A, again, there is no change in height, right? MGY is just 0 for object A, right? So there's no change in height. And then for object B, is there potential energy from gravity? Not the way we have it defined, right? The way we defined it right here, YB1 is 0, so there's no potential energy from that guy right there either, okay? So that's it for our potential energy. This is all the potential energy. That's this term. Okay. That's equal to no kinetic energy. So then now everything's gonna be potential energy. So we're gonna have the spring stretched. So let's do that one. 1/2 K S2 squared plus Nothing from object A, right? Again, object A is not changing height, so there's no potential energy in height for that, but we are going to have a change in height here from object B, MB G times YB2. Oh, okay, yep, right. All right, so that's all the V2. So it's going, that's everything we need. Again, sometimes it's nice just to highlight what it is that we're after. Watch this move here. Green's my favorite color. Yeah, I highlighted it. We're after that guy, right? That's what we're trying to find, right? So again, we're looking at this. This is the only equation we get. This is it, right? Only equation we get. So at this point right here, we gotta make sure we have enough things going on, okay? Right now, we do know something. Technically, I don't know the velocity at A, which means I don't know the velocity at B, which I don't know. I do know S1, I do know K, I do know S2, I do know K, I do know that height right there, right? So technically, if I can relate those two. I could relate the velocity of A and the velocity of B. If I couldn't relate the two, then I wouldn't be able to solve this problem. I have two unknowns. I would have VA1 and VB1. Those are both unknown to me. Right? I don't know either one of those. Well, look at the one time I go over here, you're yawning. See, like nobody was yawning on this side. Right? These things are, does that make sense, right? If I didn't have those kinematic relationship, if I didn't have the kinematic relationship that VA1 is equal to VB1, I couldn't solve this. But I do know those are the same. And so that's really just the same unknown in that case, right? They're both just V. Okay, so at this point now, right? Let's plug in all our values and solve for this, right? Because we have everything that we need. All right, so this is 1/2. Oh. 1/2. The mass of A is 2. I'm just going to call this V. I'm going to drop the A and the B because they're the same. Plus 1/2. Oh, MB is 4. Right? V squared. Plus 1/2. K was given to us as 400. S1 we calculated earlier to be 0.3 squared. That's equal to 1/2. Again, K is 400. S2 squared is 0.743 squared plus mass of B is 4 times G. Oh, what is the units? So these are real units. Yep, times 9.81 times negative 0.8. Okay. And again, it's negative 0.8 because it went down for that state. Okay? So I wanted to show you too. I could have set my datum, right, as this being 0.8 and this being 0 down here, right? And if you would have done that, this term would have been positive on this side of the equation. That makes sense. So you get to pick whatever your datum is, right? And if you put it on that side, just be careful of the positive and the negative, right? So in this, you just boop, 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 enter. It's like calculating, right? And out pops the answer, right? Please do this. Please learn how to do this, right? Because if you were to do this algebraically and all the steps that would be involved and all the mistakes you're going to make along the way, just learn how to do that. Just boop, 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 solve for V, and then it would spit out V is equal to 4.5 meters per second. Technically, it would be plus or minus 4.5 meters per second. Then you got to apply a little kinematics to it to decide if it's going to the right or to the left. Right? In this case, it would definitely be going to the right, so you can do that. That's your solve step is just doing that, right? So they're like, what should I write down on an exam when I'm doing it? Well, I mean, I would get down, like I would write, this form. Oh, I would write this form of the equation, and then I would expand it in this form right here, and then I would write it like this, and then I would give the answer, right? Because you want partial credit, right? I mean, I'm assuming you want partial credit, so you should write down like exactly what it is that you put into your calculator, and then your calculator, if you have a TI-89, it'll tell you what you put down right in front of it, and then you can see if you made mistakes and stuff, and you can double check it. Is it who here has made the jump to 89? If you regretted it in any way. Damn straight. Has it changed your life? Is it life altering, right? It's life altering, right? I say, do what you need to do to get one, right? Deal some drugs, right? Right? Steal some stuff, like whatever you need to do. Like it's gonna change your life. I know. It's funny, but you guys, you may not realize this, but you're really poor. You're really poor. You're living in a state, you don't know you're poor, and then you get out of it and you're like, oh shit, I was like really poor. Because my wife had this conversation once. It was just like, I just feel like, we're really been blessed because I've never really struggled. And then I look back at like where we lived before, like in the Seattle area, and I'm just like, I was like, holy shit, we lived in a shithole, right? And our house was really small, or our apartment was really small, and you hear all the I was like, oh my god, we were poor, right? I drove a Geo Prism. Like, how did I not know that I was poor when I drove a Geo Prism where the whole right hand side was smashed in because I bought it because it was totaled from a friend. The insurance company paid him his total, and I bought it from him, and the whole side was smashed in. How did I not know then that I was poor? Yeah, but I didn't. I didn't know it. But try to get one, honestly. It's not required, but it honestly will make your life a little bit easier, especially as you move forward in life in general. Okay. Let's call it there. I don't want to start this new topic right now. So come tonight. That's it, right? So that's this is a new topic. This is the next topic. This is impacts, and I don't want to talk about that yet. So we'll cover that on next Monday. And so you'll do the exam on Friday. I usually will have that graded by sometime Monday or Tuesday, and then Wednesday we'll go over it. So if you're missing the exam for whatever reason with a really good excuse, I want them done by Tuesday so that I can go over this exam on Wednesday. So, cool. All right, good luck.